Okay, today we're going to write the function to do the orbit tree, and in a second I'll redraw the diagram since I wasn't smart enough to save it. I actually spent an hour just now trying to record a video explaining group theory. We're going to need that eventually. So I wrote up this outline for myself and I started trying to record it, and well, you can see sort of how long the outline is, and it was taking way too long. I didn't prepare exactly what I was going to say at what time, so I'm going to do that this week and try doing this group theory intro next week. For today, we're just going to write some code. Let me zoom in. I always forget to zoom in. All right, so let's recall what we're doing here. I forget which example I used last time, but we may as well use the Rubik's Cube example. And actually, there's a nice diagram that I saw on the internet the other day, which I can use for this. Yeah, this one. So, what this is doing is it's giving a number to each of the positions on the Rubik's Cube. Sorry, let me zoom in. And the generators of the Rubik's Cube group, that is to say, the allowed permutations that I can do with the Rubik's Cube in my hands, are here. So let's just go through this first one. Okay. I've labeled all the positions, or someone else labeled all the positions on the cube, and if I turn the top face clockwise, okay, and in your mind you have to wrap this into a cube. If I turn the top face clockwise, it takes the item at position 1 and moves it to position 3. It takes the item at position 3, moves it to position 8. Takes the item at position 8, moves it to position 6, item at position 1. Same thing, 2, 5, 7, 4. And of course, again, in your mind you have to imagine the Rubik's Cube. It's rotating, you know what? None of these are actually any good, by the way. So I'll try a new one. So say this is the top face, all right? Oh, this one's pretty good, actually. You can see that it's also moving the stuff on the first layer. So, oh, what have I done? Wrong way. It takes 17, all right, and it moves it to 9, which moves it to, it's hard to imagine this. If 9 is over here, it will go here, which is this one, 33, and it takes 33, moves it to 25. And so on for 10, 18, 34, 26, 11, 19, 35, 27. Oh, look at that. 9, ooh, did I get it wrong? Oh yeah, I did get it wrong. Stupid. Oh no, I didn't get it wrong. I just started on the front, but normally permutations are written with the smallest number first. 9. Okay, 9 would be this one here. If this, sorry, I made this the top face, didn't I? If this is the top face, 9 is this one. I don't know if I need to explain it in this much detail. I mean, people watching this probably understand this stuff, but I think it's better to be explicit instead of not explain anything. So let's say top is the blue face, left is the white face. Let me actually put it on top. Okay. Then that would mean that the front face is red, the rear face is orange, and the left face, or sorry, the right face is yellow. Okay. Top, front, left, rear in the back over here, and right over there. 9 is this one here on white. If I turn the top face clockwise, it goes to this position here, which is, wrap this around in my head, 33 on rear. 9, 33, 25, 17, okay? I think that's enough for anybody to understand what this means. These are our generators, okay? And if we are trying to think of the orbit of one, which is this blue sticker here, what are all the places it can go? Well, it can go anywhere on the top face. If I move it to the front face, it can go anywhere on the front face. Come on. Ooh, come on. Okay, and then, you know, I could also move it anywhere on the, come on, left face. Okay, you get the point. The orbit of one is all the corners, as it turns out. But how could we get the computer to figure this out? Well, what we're going to get it to do is build this tree. I've already explained this before, but I'm doing it again because it's always better to have the diagram. And anyway, I've already started. So if we call this turning the top clockwise, if we call that U, okay, U is equal to okay. Let's just get rid of this extra junk that we don't need. Okay, this one here is U. I actually got to figure out which ones these are. This one here turns left. 17, 19. That's front, or forward, some people say. 25, 27, 25, that's right. 33, 35, that is back. And that means this one is down. Okay. What we are going to do is build this tree explaining how 1 can go to any position on the cube, or well, rather any position in its orbit. It can only go to the corners, obviously. So one thing that we decided we were going to do, and there is no reason for this right now that you know of, but in the future I am going to need it to be this way to actually write the cube solver. Instead of saying how do I get from 1 to any element, so for example, if I go from 1 and apply the up permutation, I get 3. And if I go from there, I can apply forward. No, I can apply back and get from 3 to, I don't know, one of these. You know, maybe it's 27. I'm not going to figure it out, but instead of doing it like that, instead I am going to have it built that it tells me how to get from any position back to 1. Again, there is no reason for this yet, but there will be a very good one in the future. Okay, so that means that we're going to do a breadth first search. Okay, essentially this makes a graph where the edges are labeled with any of these permutations or their inverse, and well, this is a graph, and we're specifically building a tree. And you know, I'm going to make up some numbers here. I'm very bad at drawing with the mouse, but you know, maybe it looks like this or something. Okay, and I forget what I was saying. Man, I am super scattered today. I'm not releasing the videos I recorded earlier because they are even worse. This one is the best one so far. But anyway, we are building this graph. Okay, that's our goal. oh yeah, I was talking about breadth first search. Yeah, so we're going to search all the edges of 1. Basically what that means is we're going to apply all of the allowed permutations and see where it takes us. And then we're going to do breadth first search from there and breadth first search from there. Okay. The reason we're doing breadth first search is because it will give us the shortest path from any element back to 1, or any element that it can go to, that is. Something from algorithms and data structures is that if all your edge weights are 1, then breadth first search does give you the shortest path. Okay. Also, breadth first search is pretty easy to code in. So that's what we're going to do. Okay. Great. So I started making this object here, or this function. I started by saving the namespace in this variable. I'm actually just explaining this to myself because I wasn't smart enough to leave comments for myself. I am making a I am making the vector that we're going to return. Now, oh yeah, that's right. So, okay. Ret will contain the Shreier tree. I had better redraw the diagram for a Shreier tree. Supposing that I'm just putting random labels on here, these are not correct, unless there's some incredible. No, in fact, I know they're not correct because I don't think 5 or 8 or I don't think all of these are corner pieces. But just suspend your disbelief for a second. Okay. The just a fact from trees is that if I just keep the parent pointer in each element, that completely describes the whole tree. That's what we're going to do. So I'm putting the indices up here for reference. I'm going to skip a few, 27, and skip a few more all the way to the end. Okay. What is the parent of 1? It doesn't have any, it's the root. Okay. What is the parent of 2? Well, let's pretend that this is the entire orbit of 1. Again, this is not correct. Maybe don't think of this as the actual orbit of 1 in the Rubik's Cube. Think of it as the orbit of 1 under some strange permutation group, which I haven't bothered to define yet, okay? Parent of 2, it doesn't have a parent. But the thing is that 1 is actually in the tree, but 2 isn't. So we're going to distinguish it like this. I'm going to say that I'm going to put E for 1, and E means the identity permutation. We're going to think of this vector as saying, which permutation do I apply to get back to 1? Okay. Is there any permutation I could apply to get from 2 to 1? No. So we'll put a null here, for example. How do I get from 3 to 1? I apply U inverse. How do I get from 4 to 1? I can't. How do I get from 5 to 1? I apply F. How do I get from 6 to 1? I can't. Okay, so you get the idea. This is going to be what we're going to return. And this is the Shreier tree. It is named so because we're going to use it in an algorithm which is due to Shreier and Sims, I think. And I might have to look that up to know for sure. Okay, so queue of nodes in the tree. And you know what? It's a queue, and I called it frontier. I think that's good enough. And I'm just going to perform right for search. Actually, I doubt it, but I wonder if there is a BFS NV STR. Wait, what? Okay, I got distracted. I have the feeling that yeah, so we're gonna code it ourselves. I had a feeling that there wasn't already an algorithm for it. So to perform the BFS, we go, we constantly pop the next element, and we now want to see all the places where this element goes under the generators. Okay, one thing I would like to do is, oh no, never mind. Okay, so for each of the generators, int dest is equal to current through that permutation. And oh, fascinating. I would really like to have labels for my permutations, right? I want labels in this Shreier tree. Why? Because when I go to solve Rubik's Cube, I want it to be listed in terms of the movements. I don't want it to give me some random string of numbers that I can't understand. So I'm actually going to add that in. This is where delegated constructors is really nice. Let me label some of these. From cycle notation in new namespace. In another perms namespace. From cycle notation in a particular namespace. From tabular notation in a particular namespace. And now I need to yeah, so yeah, thinking. Tricky. Because I want it to be possible to not give it a name. Yeah. Okay, I see it now. Yeah, like this. String name, or maybe label. And it's getting too long, so I have to do this, which I don't particularly like, but and what did I call it? Label. And a particular namespace with no label. This is going to call Should I give it an empty string? Yeah, I guess that's okay. What I should do is give it no label. I think that'll help us track down problems later. And actually, I'll just put NL to make it a little bit shorter, because I have a feeling we're going to see this a lot if I make too many mistakes. With a particular label. And we also need it for this. Actually, maybe it would look fine like that. It really doesn't. I hate that even more. Okay, this is the least bad. Oh, yeah, okay. I got this. Actually, these delegated constructors are super handy, but a little bit tricky. For some reason, I find it hard to get my head around it. Quickly, that is. Like, I get it, obviously, but it's kind of hard to get right the first try. I'm half tempted to automatically generate these to be unique, but it's probably more trouble than it's worth. I mean, you know, we don't want to sit here all day. Actually, I kind of do want to sit here all day and work on code, but I got stuff to do. Okay, let's see if this still compiles. Oh, good. Let's see if it still works. All right, excellent. Okay, let's move on then. So we see where this takes it, and then we check. So this is a bunch of null permutations. If ret of dest, we discovered a new element in the orbit, and so now we'll do ret of dest is equal to p. I mentioned this last time. Alright, I'm getting into the swing of things now. Maybe I just had to kind of wake up properly. Okay, so 7 to get from 7 to 1 is this D permutation. To get from 8 to 1, it would be RF, but it's actually enough for us to just write R. Because what we're going to do later when we actually traverse this tree is let's say I want to get from 8 to 1. I look up 8. I apply R to 8. That takes me to 5. 5 isn't 1 yet, so I apply F to 5, and that takes me to 1, and so I'm done. So that's how we actually use this tree. So it's enough to just do this. Okay, great. And I'm also going to do the same thing here. Yes, but I'm going to do it also for the inverse. Oh, interesting. Maybe I should have this print the label. No, I shouldn't. But yeah, how do we get the label for the inverted one? Well, it would have the same label, wouldn't it, right? Yeah, it would have the same label, it would just be inverted. So if we ever print the label, we'll also use inverted to, you know, maybe append it with a -1 or with a prime or with a lowercase I, which is what's usually done in Rubik's Cube notation. So here I wouldn't call it U inverse, I would call it UI. Maybe that's what we'll do. But I'm happy with this. So we're done with the orbits function. That's all it took. I can't believe that was it. I mean, we'll test it obviously. So I lost. Where is it? Oh, right here. Okay. Now we're also going to do it. We're going to do this minus p, like that. Let's see if it compiles. Okay. No match for operator minus n minus p const perm. Oh yeah. This is const and this is const. Oh, sweet. This is also const actually, so let's put it on. We're not calling that orbits function though, so I don't know why I'm bothering to run the program. Okay. Let's where the hell did I put that page? I'm not going to do this by hand. Someone's already gone to the trouble. Yeah, so we're finally ready to start using the real Rubik's Cube permutations. So we're going to do, let me just paste this in and we'll add the stuff around it that we need. Oops. So perm u build permutation for cycle notation in a new namespace. Oh, I also need to make one for with a label. Yes, that's right. And this also has to in a particular namespace with a label. Oh yeah, look, P and label, like that. I need that. So this is in a new namespace with a particular label. Okay. Actually, oh yeah. Let's do it like this. Let's do shared pointer to nmap Rubik's that for all of them. Let me just make my life easier here. I'll replace these when the time comes. I'll replace those when the time comes. It's a little bit too long to fit on the screen, but that's okay. Ooh, spaces. I should. Oh, I already did it. Hey, good for me. Okay. So this is now going to be. Now I gotta redo all that work. No, I don't. Actually, I already did it here, didn't I? LFRBD. LFRBD. Come on. Okay, great. Let's just see if this compiles. Okay, great. Now, let's ask for the orbit of 1 in the Rubik's Cube. I mean, this is going to be awesome if it works. So, we're going to do auto S tree for Shreier tree is equal to orbit of 1 in. You know what? Let's do this. Vector of perm Rubik's gens. Maybe let's call it gens. I mean, we know what we're talking about here. And this is equal to ULFRBD under the generators. One thing I should do in the pretty printer is do something for inverted. Ooh, no, because this takes care of inversions. So in this case, I think what I will do is I'll do if p.label does not equal NL, then I'm going to do O p.label, and maybe I'll do like this. Sure, that seems fine. Oh, God, I hope this works. This is going to be awesome if it works. Well, first we'll see if it compiles. Oh, I don't believe it. I can't read that. It's because my vector pretty printer, so where do I have that? Right here. I don't think you can do template special. Oh no, you can't do partial specializations for functions. It's going to be the exact same as this one, except it's going to print new lines, and it's not going to do the. It's going to do this. And it's going to do this. It's always a new line, isn't it? It's always a new line and a tab. Thinking. let's see if that compiles. Yeah, I figured as much. I always forget how to do this. Oh, yeah, I just need to forward declare the struct. Almost there. I need to forward declare this. Okay. Ah, there, that's better. Huh, first try, look at that. This looks weird. Oh yeah, okay, I haven't done the whole BFS yet. I knew it was too easy. But actually there's something wrong here. We're missing, like, this doesn't look right. So we've got a bug when it comes to larger permutations. Let's let's just look at U. That is weird. What do we have? 1, 3, 8, 6, 2, 5, 7, 4, 9, 33, 25, 17. You know what? This looks like no accident, because this is where the spaces are, that it didn't work. In fact, it might be picking up the space as the... No, it is not. It's picking up an empty element name. It is picking up an empty element name. And then it gets 1, 3, 8, 6. So there are two problems here. It's picking up an empty element name when there's a space, and it is not picking up the left parenthesis properly. Okay. We're gonna get there. We are gonna get there. Which function is that? String. This one. Right? Yeah, this one. Yeah. We can change this for this is a little known feature of C. Because I used a macro for delim, this is actually going to expand to this string. But in C, and also C++, if I have two strings next to each other like this, the C++ compiler automatically concatenates them like that. So this is a neat little trick I can use. So let's see if that gets rid of the empty elements. Oh, that seems to have fixed everything. No, it didn't. These only have 3 in them. These are the ones that don't have a space. Let's also just confirm that by printing out this one here that has spaces at the end, which is F. That's weird. It seems to get the first 3 right in both cases. I think we need the debugger for this. Oh, and oh, you know what? I know it looks like the first 3, but because F is in the same namespace as U, the order is bizarre. Let's just look at U here and see what happens. 34, 26, 18. It's skipping 10 and it's skipping 11. Let's put a space in front of them and see if that fixes it. That'll let us know if the space is the problem. Yes, the space is the problem. So our quick fix didn't completely resolve the issue. Let's think about this again. That shouldn't happen. Yeah, let's put this through the debugger. That'll help. So we are at line 124. Do I have a CMD open? Whoops, what did I just do? And we want to go to line, let's put it at line 120 and start from there. And go. I don't know why it's making a bunch of threads, but anyway. Okay. We're at line 121, char pointer, talk. Okay, next, step in. Okay, print token. The token is just that guy. Oh, I see. So it caught the space and it made this the token. So the token is just the left bracket, not the left bracket and everything up to the comma, which is what it's doing over here. Yeah, okay. And let's actually add a breakpoint at this line. And I forget how to do hooks in GDB. You know, I'll just do it manually. Okay, so the first 4 are correct, right? So if I do continue and let's talk, we get, oh yeah, shoot, that was dumb, that was dumb. That was dumb. Okay, hold on. Delete breakpoints. Restart. And I just want to break at line 124. And go. Okay, next. 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 So yeah, this is what we want to see. So yeah, and then if I do next and print talk, it should just be 1, which it is. Okay. Okay, you know what? I've never done this before, but watch points is exactly what I want here. So let's see how to do it. Okay, perfect. That's what we want. Let's delete all breakpoints, and we're gonna watch talk. And that's really nice. I'm surprised it was that easy. We went from 1 to 3, and let's go over here. Then if I do this, from 3 to 8, from 8 to 6, oh, this is really clean. Now, we should get a left bracket, which we do. Then we get a 2, then a 5, then a 7, then a 4. Should get another left bracket, 9, 33, 25, 17. Now, we're going to get left bracket and the number 10. Okay? Oh, yes. Right, string talk starts at the end of the current token. Starts at the end of the current token. And by the way, string talk has already made this comma into a null character. Shoot. So my little quick fix is not as good as I thought it was. So yeah, I see no other way to do it than to just keep incrementing talk until we get to a non-delimiter character. And to do this, we are going to use strcr. I don't know how people say it in their heads, actually. C++. Strcr. First occurrence of character in string. Maybe I want something else. Let's see, do we have? What's this? I've never seen that before. Oh, no. Actually, I don't know what some of these do. Last of occurrence of character in string. Oh, interesting. I've never heard of this function before. Returns the length of the initial portion of string 1, which consists only of characters that are part of string 2. Sounds like what we want. Length of the initial portion of string 1. Okay. Instead of doing strtalk, instead we are going to do talk plus equals strspan of talk and our little trick. Let's try that. Still didn't work. Yeah, it's still matching this space. And I find it odd though that we're not getting another left bracket. I wonder why that is. I'm thinking about it. Why is that the case? Well, we get a left bracket when the first element is a left parenthesis. I really don't know why. But here, I think we probably need the debugger. Yeah. So quit, recompile. We're gonna use watch points again because that was awesome. Talk isn't in this namespace, or in this scope, I should say, not namespace. So I don't know if we can just do watch talk. Yeah. So let's break on orbit. No, not on orbit. This is no. Fine, we'll do it the easy way. Okay, so the old value of talk was the left bracket. Unsurprising. The new value yeah, right, because the string span doesn't go all the way to the comma because it stops at the space. Okay, well, I was trying to do something really fancy by trying a new library function, but it turns out that I think we just need spaghetti code, because if the number is right after the left bracket, then we want to go to the next token, as in call string talk again. But if the number does not start right after the left bracket, then the left bracket is by itself in a token. Okay, I think I got this. Let's, wait, what is this? Yeah, let's put this back the way it was. If token1 is null, yeah. Let's try that. Yeah, perfect. 1386, let's just check that's right. 2574, 933, 2517, 1034, 26, 18, 1135, 27, 19. Okay, I did some funny C stuff here, so let's talk about that quickly. Here I incremented the pointer and asked if that was the end of the current token, as in if it was just the left bracket by itself in a token. If that's the case, we need to move to the next token. Otherwise, we increment token past the left bracket. But the trick here is that I had to increment it anyway to see what was after the next bracket, so I've already incremented it, so I didn't have to write anything under here. As in, if this condition failed, we have already performed the necessary action to check the condition. As in, checking the condition performs the action that we would have had to do if the condition didn't hold. So that's why we didn't have to write anything underneath it. I like doing stuff like this. This is my personal project, so stop judging me, okay? Great, so we haven't finished the breadth-first search yet, but I'm really pleased that this stuff is working out. Now, I'm a little bit concerned that it's not grabbing the inverses. Actually, one thing that I'd like to do in here is also print out the index, just for my own reference. For each one of these, int index starts at 0, I'm also going to print I star I dot names of the index, like that. Oh, that is really annoying. Fine. Segfault star I dot names at index. Why is that failing? By the way, I forgot to do this. Not that it would have caused a seg fault. Oh. That's weird. Why are we having a null pointer? I see. Because we don't have a namespace in the empty elements of the vector. So I guess, shoot. Okay. If I else that's kind of funny. That the index and the names are actually they look like numbers, but they're really strange, so it's kind of confusing to look at it. The index 9 is not the same as the thing represented by the strain 9. Let's see if this is right, actually. We'll deal with the inverses in a second here. Exit. U takes, Okay, well, we have some problems. By the way, the arrows have to go backwards, which is why I just did that. I think I had the minuses wrong, actually. Hold on. And you know what? This would be a lot nicer if it was a come on, tab character. Okay, that's a bit better. This is 100% wrong. Maybe the label I put is wrong? No. Oh, 0, not 1. Ah, yes. Right. Right. This is the integer 1, not the element string 1. Tricky. So let's add that function to look it up in the namespace, because we can do that. What does that return if the string isn't in it? Oh, it inserts? Oh no, that's not what I want. Oh, that is awful. That is really awful. Shoot. I don't want this to insert stuff if it doesn't find anything. A similar function map add the same behavior, but throws an exception when it does not. Okay. Okay. One of my random things that I find amusing in C++ is when you are able to write an entire meaningful line of code, which is all keywords. I find that kind of funny. Okay. So where was I? If names dot contains label. Actually, I want if names does not contain label. Just return ret as is. Because the orbit is empty. Makes sense. Else, int pos is equal to names of label. Oh, arrow. It's a shared pointer. It's still going to be the same result, but now I'm going to make this a string. And now we should get something meaningful. Oh, beauty-ish. Oh yeah. Yeah, of course. 1, when you apply any random permutation that doesn't include 1, still takes it back to 1. I guess that's okay. We can leave it for now. Look at that. 3. This is actually not the right direction. U takes 1, 2, 3. I actually want U inverse. Oh, but you know what? My pretty printer doesn't deal with inverses, does it? Or maybe it does. Okay, just quickly. If wait, this is not the right function. It's this one that I want. P dot inverted. Sure, good enough, right? I'm gonna make it nicer in the future. This is just good enough for a quick test. Okay, so none of these are inverted. That's a little bit worrisome, actually. I mean, so far these are correct, but all right, let's see. Let's go back to our orbit function. By the way, this doesn't have to have everything in it. You can just do return orbit pos and gens, which should still be fine. Yeah, okay, good. So now we need to fix this thing with the inverses. Okay, destination is current to the inverse. So current is always 1. Well, the element string 1, not the internal representation ID 1. Okay, the element string 1 to the power of minus p. So when we apply minus u to 1, we really should get 6 and not 3. So we need to do a little bit of checking here to see what this is doing when you apply the minus operator. And then this one when it's inverted or not. Ah, found the problem. Okay. Oh, nasty. You have to do a linear search. There's no other way. There is no other way. So what I'm doing here is I am actually inverting the mapping. So this Boolean might not be needed anymore. It used to make perfect sense when we were using the cycle representation, because finding the mapping of an element under the forward or inverted permutation in a cycle notation was just as quick both ways. So it didn't make sense to actually invert the cycle representation and just keep a Boolean and do one method versus the other. But in the tabular representation, the inverse means doing a linear search through the array. And so I figure if we're inverting a permutation, let's invert the map. Let's invert the map, and we'll just save that. This also isn't efficient though, based on the way I'm using it, right? I'm using it like this. I'm just throwing on minuses whenever the hell I want. So this is actually worse than before, what I've done just now, because it's actually building the whole mapping when I just need to find one element. But they're the same. Okay, I'm just going to leave it like that for now. Okay, we can worry about efficiency, whoops, later. Oh, nasty. Okay, this is good enough for now. Okay, great. Great. So to get from 3 to 1, we do U inverse. To get from 6 to 1, we do U. To get from 17 to 1, we do L inverse. And you know what I should do is in the pretty printer, right here, yeah, oh shoot, I have that, shoot, yeah. Okay, and let's take off the I here. Okay, great. To get from 3 to 1, I apply UI, which is equal to this permutation, which does take 3 to 1. To get from 6 to 1, I apply U. To get from 17 to 1, I apply LI. Yeah. To get from 27 to 1, I apply B. Yeah. BI to get from 14 to 1. Yeah. 40. Yeah. Is this actually what L is? Yeah, look at that. From 40 to 1, I apply L. Okay, great. We are well on our way. We're almost done. We discovered a new element, and so now we need to do frontier dot push nest. in both these cases. See how easy that was? So now we should have done it. This should be the orbit of 1. 1, 3, 8, 6, 9, 33, 25, 17, 11, 35, 27, 19, 16, 14. One thing I would like to do here is man, C++ is really nice sometimes, and this is one of those cases. Although I really wish it had something like Python's enumerate. That's bizarre. Oh. Oh, weird. Wait, how did this even compile? What the heck is going on here? For each permutation? What on earth? I never wrote. What the heck? I meant to use index here, not I. I should do P here for permutation, for each permutation. And actually, oh, you know what? I don't need this index. I can just do p.label. Right? Oh, wait, no. No, I actually did want this, yeah. Because I want to see the orbit, not the permutations. But that was super weird. How on earth did this even work? That is bizarre. Rubik's is an nmap. Somehow this permutation class must be convertible to a string or something, or an int. It's the only way. That is bizarre. I'd never seen anything like that before. Let's see what it's really doing. How do I go right to it? Come on, take me there. Oh. This. With an int. So somehow that is coming back as an integer. I mean, I don't need to know this, but this is really strange. So it is returning a string. the string associated with 3. Wait, no. It's returning an integer, the int associated with 3, which is 1. That is so weird. How is that happening? Look at that. It is converting it to a Boolean, which is converting it to the integer 1. Well, you know what? I don't like that. So here's what we're going to do. I think what you can do is you can do explicit operator int equals delete. Disable implicit conversion to int via bool. I don't know if this will compile. Yeah, look at that. Oh, wait, but this still compiles. This still works. What the heck? How? Oh yeah, because the conversion to bool is implicit, and I can't. That's right, I can't turn off a implicit conversion from bool to int, but I don't want to turn off implicit conversion to bool, because then I wouldn't be able to write this. I'd have to do if bool of p, and that would be awful. Okay, fine. What if I do this? Yes, perfect. Yes, perfect. The thing I like about C++ is that if it compiles, it's... Use of deleted function per operator int. Really? Ret is a vector of perms. When I index ret with an int, I get a perm. And this is the Boolean not function. This is line 281. So it should be near there and here. It didn't change much. This. Perm operator Boolean. That's what it should do. And then XORs it with 1 to invert it. Weird. Super duper weird. Let's add that line in here. Well, there's nothing we can really do about it. This shouldn't disable conversion to bool. But that's not the Boolean one. But let's see if it works. Yeah. Oh, wait. Maybe it's this? No, wait, no, that's ridiculous. Come on, I'm better at C++ than that. Logical not. I want logical not. Logical not. Why? That is so weird. It should be making it a Boolean. Is there an implicit keyword? No. Oh well. I guess we'll just have to live with it. Oh, actually, what we could do... No. Yes. Yeah. What we could do is this. Operator int const. And what we're going to do is we're going to do... Okay. Oh. Darn. Alright. I'm done wasting time. Well, I mean, it's my free time. I'm not really wasting it, am I? But, there. So this is the orbit of 1, apparently. So, orbits. Perfect. One, 3, 17, 14, 8. Oh, you can't see this, but I'm tracing with my finger on the screen on the ones from the gap results. 38, 9, 41, 19, 48, 22, 6, 30, 33, 43, 11, 46, 40, 24, 27, 25, 35, 16, 32. Okay, this has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 24. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Ah, darn. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Yeah, 24. Okay, that's correct. It is correct. Super duper cool. Super cool. Well, I guess I finished that. Now what am I gonna do? I just had a really cool idea. In this permutation that we return from the multiplication operator, we should names new mapping and check this out. Label plus other.label. Yeah, look at that. So now if I do cout u times f times u inverse. Oh, shoot, I forgot about the inverses. Okay, string new name if inverted name plus string new name equals label if equals I new name plus equals dot plus other dot label if other dot inverted new name equals I and new name. Oh yeah. Oh yeah, look. Looks wrong though. Yeah, that's weird. The name is right, but the permutation is wrong. Damn. My permutation multiplication function doesn't work, does it? Well, let's just try this first. Okay, that's okay. Is that's not correct? Or maybe it is. This should have order 15, I think. Or not 15, 105. 1, 2, 3, 4, 5, 6, 7. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 12, 13, 14, 15, and 3, yeah. And then 1, 2, 3, 4, 5, 6, 7, yeah. Order 105, as expected. I just know that, by the way. I didn't have any mathematical trick. I've done this before. So then, how come? Let's do perm p is equal to u times f, and then let's do p times f. So far, so good. P times u. Ooh. Weird. Let's take a look at the multiplication function. Oh, look at that. That's not correct at all. Where are we getting that big uninitialized value from? I see, says the blind man. Yes. So, if our mapping size is less than the other's mapping size, no, this is fine. We're gonna get to the bottom of this. Actually, yeah. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20. Okay. I should check F dot mapping as well. So the largest element in here should be 38. Yeah, that's fine. The largest element in here should also be 38. Let me look more carefully. What this looks to me is we're indexing a smaller vector with one of the indices in the larger vector. So let's take a look at the code and see if that could possibly happen. Yes, it can, right here. Actually, I just realized something. You remember that? Yeah, you remember this guy? We can use that. Well, it didn't crash this time. Ooh, that's weird. It might be right though. Real quick. Do I have gap open? What do you mean syntax error? Oh, it must have been a hidden character. I didn't see. Okay, so u times f times u inverse. Alright, let's see how close we got. Ugh. I must have closed it like an idiot. So 3, 30, 41, and then it goes off the rails. 27 shouldn't be, oh, 27 is in here. 27, 24, 22, and then 26, 21, 23, it's so close, 20, and then randomly 19. So our function to print out the permutation, I think, has an error, but I also think the mapping might be correct. So this is going to take a little time to check by hand, but we can do it. Okay. 1 does not move. 2 goes to 39. Not correct. I know, wait. Oh boy. 0 means, oh yeah. Yeah, I have to convert these to, well, irritating. Irritating. But I don't actually want this, I want a little bit better. 1 goes to 1. 3 goes to 30. 30 goes to 41. 41. Oh, these aren't in order. That's annoying. 41 goes to 11. Oh, that's not right. Damn. Okay, now it might be a good time to push what we have so far. How are we going to fix this? 5 goes to 28. 33 goes to 43. So far so good. 25 goes to 27. Yeah, and let me put this a bit closer. It's hard to jump. I just realized this text is minuscule. You probably can't see this at all. But I need to see it. I don't know how to make it bigger, so we're gonna have to live with this for now. 11 goes to 11. Hey, no wonder. No wonder they're pretty. Okay, so the pretty picture is actually probably fine. 19 should go to 3, but actually for some reason it's mapped to 11, which it shouldn't be. And the problem with that is our pretty printer assumes that that it's a cycle. If 19 goes to 11, but then 11 goes to 11, it doesn't ever come back to 3. So that's what's wrong with our pretty printer. Is that nothing's wrong with it. It's just our mapping is all foobar. So how do we fix that? How do I even begin to fix that? Why? Let's take a look at the multiplication function. This seems suspect. What time is it? Oh my god. What? No way. I've been recording for 2 hours. That's in addition to the hour I spent earlier of stuff that I'm not going to upload to YouTube. I have stuff to do today. But I want to fix this. Let's fix it. I don't have good enough discipline to do the work I should be doing. And, well, I mean, that's not true. I could go, but if I don't fix this, it's going to bother me, and it's going to be much harder to fix it in the future, because right now everything's sort of still in my head. And anyway, the stuff I'm doing at work today, I can do it late at night. Like some jobs, you can't do it late. But this, what I'm doing is I'm following tutorials and you know, doing stuff in Vivado and that kind of stuff. I can do it late at night. You don't really need much thinking. It's just click and drag in the right order and fix errors when they come up. So I can get away with it today. Also, this is my last chance to do this before I go away for 2 weeks. So I want to fix it now. I don't know why I have to justify this. Well, one thing we could do well, that seems to have fixed it. It's not as efficient, by the way. We can do better. And actually, I do want to do better because permutation multiplication is something that's going to happen a lot in this program. But I think that's correct. So we'll figure out what's wrong with our more efficient method in a second. 3, 30, 41, 19. 8, 33, 43, 16. 5, 28, 42, 13. So far, so good. 20, 20, 26, 21, 23, 22, 25, 27, 20, 22, 25, 27, 24. Yeah, okay, this is correct. Okay, so what's wrong with our more efficient one? Alright, let's do this first case. If our mapping is smaller than the other mapping, then everything's easy. Because our mapping right here will never take us out of range of the other mapping. So we do all the ones in our mapping, followed by the other mapping. Then for these other ones, we don't have to do mapping of I because we know that when we're larger than our mapping, mapping of I is equal to I implicitly. It's not actually in the vector, but that's how we define it. So this looks fine. Okay, that looks fine. I'm going to go ahead and guess that the problem is in here. Now, here we're going to do, I'm going to write it out explicitly here, is equal to mapping of I if temp is greater than or equal to other int other dot mapping dot size new mapping of I equals temp. Otherwise, new mapping of I is equal to other dot mapping of temp. This should be right. This should be right. But it's not. We have the same problem. Weird. Super weird. Okay, let's do a little example. Maybe that'll help. Why am I not using the debugger? Because I don't see a quick way to set this up for the debugger. Okay, let's say we have, I don't know, 3, 2, 5, and I'm suspecting that the bug is in here when the other mapping is smaller. So we're going to do times 0 to 1. So temp is equal to mapping of I. Temp is not greater than or equals to other.mapping.size. So we get that the new mapping is equal to other.mapping of 0. Okay. Here, temp is equal to 1. Same thing. New mapping of 1 is equal to 2. Right, this condition did not hold, right? So 1 goes to 1, goes to 2. New mapping of 1 is 2. Same thing here. It's 2. New mapping of 2 equals, oh sorry, temp is equal to 4. This condition does hold true. So the new mapping is 4. Okay. Oh, I think I just understood the problem. Let's go ahead and do it though. Right? So 0, 1, 2, 3, temp is equal to 3. New mapping of 3 is equal to 3, right? It's equal to temp because it's larger than or equal to the size of this. But here is where the problem's going to happen, and I know exactly why this is happening. I just need to put it in words here. Let's do the example first, because if I explain it badly, at least the example will help. Temp is equal to 2. Oh, we are just doing, oh, I shouldn't do temp is equal to 2. We're just doing straight new mapping of 4 equals 2, but that is not correct. We can't get around it. We have to do that. We have to do the conditional for each one. See, the reason this is more efficient is we don't have to do the conditional for each one, but we can't get around it here. The reason being that even if I is larger than the size of the second one, we might still have an element that maps into it in the first one, even when I goes past it. So we can't make the assumption which makes it more efficient, and we have to do it the brute force way. But that's okay, because now I think we have solved our problem. Hopefully. Yes. I think that's right. Yep, we did it. Okay, great. So let's get rid of this. Our stuff is good to go. Let's push it to Git. I'm really tempted to keep working on this because I've made so much good progress today. Okay, maybe the last thing I'll do before leaving is I'll start organizing this into separate files. Because what, we have almost 400 lines in here now. So first, which files. Oh, and template specializations are really awkward when it comes to splitting up among files, but I always forget how to do it. Well, let's just do it, so. Okay. Oh, hey, I forgot I did this. I could have been using that. Should I make this nmap in a separate file? Or should I make it a static or a private struct just for the permutation file? Could this be used for anything else? Yes, of course it could. Yeah, you know what? I will make it its own file. Okay. What else do we need? I think that's it. Oh, this template stuff is really nasty when you put it into different files. I guess we'll just do this stuff one by one. Let's see if this still compiles. No, of course not. This always takes forever. This should still be on my clipboard, actually. Oops. Oh no. I need to make a makefile now. Ugh. That's the price you pay for organization. Whoops. These are my recordings. These precompiled header files will cause you headaches if you forget that they're there and you try to compile stuff. Believe me. Maybe I should just make a makefile. Oh, hey, that compiled. Okay, good. Fine, let's bite the bullet and do it. I actually never remember how to make these. I guess I'll just call it perms. This is going to need main.o, perms.o, map.o. I think you can do this. I think you can do that. know what? Let's just go ahead and make our lives easier. We'll add debugging symbols, why not? Is it an underscore? I think it is. Oh, no, it's not. This fnode diagnostics show correct turns off the, if you have an error, it'll also print a little caret on a new line underneath it to point exactly where the error is. I never need that. It's never helped, or rather it is helpful, but I never need it. It's more than, I can look at the error and know what the problem is. And it just clutters it up, the screen. It's already long enough with all the template crap, so. Okay, now cross your fingers. Okay, great. And okay. Now let's go into this folder and do a little bit of cleanup. I don't need this anymore. I don't need this anymore. I don't need that anymore. Wait, I don't need that anymore. I'm hanging on to this for next week. Now, well, let's do that when I'm done editing. Okay, now this perms.h is going to include oh, how much do you want to bet this isn't going to work? Okay, what do we need? We need this. I don't think we need pair, actually. Okay, let's just do them one by one. We need memory for the shared pointer. We need vector. We always need vector. We need string. We need... I'm going to move orbits here in a second, but I'll do that in a minute. Whoops. Okay, let's let the compiler tell us the mistakes we've made. Oh my god. I don't know why make share is in utility when shared pointer is in memory. Whoops. Okay, max is in algorithm. Standard, yeah. Ooh, we're getting there. Oh yeah, this dlim is gonna go into parameters.h. We're getting there. The worst is yet to come though. Max was not declared. Standard. Whoops, I always forget about that. Almost. Iota. Standard. What? Yes, it is. Okay, good. Good. Almost. Let's take these and put them in there. I think anybody's using set. Okay, good. Now, for the pretty printing. You know what? I use these two functions. I retype these like 50 million times a day. I should really just make a global header. Okay, for now I'll just make it a local marco.h, but I'm eventually going to move this to my global header directory as soon as I figure out how to do that. to see all the specializations, right? Oh, this isn't gonna work. This isn't gonna work. I know it. Oh, it did work. It shouldn't have, because I know that as soon as I know what's gonna happen. As soon as I move this, I'm gonna have all kinds of headaches. This actually could also go in Marco.h. Okay, this, I could make it a friend function, but let's see what happens if I put it in the CPP file, which, by the way, I'm pretty sure is not going to work. Yeah, okay. Oh. Why did I put that? Wait. No known conversion from a string, basically, to a perm. I don't think that's the problem. Oh, maybe it is. I don't believe it. Oh my god. Okay, maybe this isn't going to be so hard, but this one here is going to be the killer. I just know it. I just have a bad feeling. Now, how do you do a prototype for this? Well, let's just do it in the usual way and see what happens. Yeah, templates and header files is a recipe for disaster, although let's just try including Marco.h here and see if that helps. Because to specialize a template, the compiler has to know about the unspecialized one. Compatible definition of EL. Yeah. Yeah. I don't think this is gonna work. Huh. Well, we managed it. We managed it. Okay. No. Ooh, we gotta get rid of that precompiled header. Don't want that kicking around. Fit status. Out of shape. Okay, good. Now, maybe I should put this on a public GitHub. I mean, if anybody is watching, they probably want the code. I don't know how to, I mean, I do know how to do it, but I always forget. Is this gonna work? People shouldn't look at my email. Okay, done. Okay, so let's do a new repository. Rubik's Cube Solver. Should give it a more catchy name, but I like it when the name is its own description. No. Yeah. Let's just do that. Huh, that was easy. Yeah, look at that. Okay, well, I guess I'll add this link in the video description, and you can take a look at the code at your leisure. Yeah. You see that? Yeah. Yeah, I'll keep updating this as we do the series. So, okay. As much as I would like to keep working on it because we're so close to doing some really cool stuff, I think I got to take off. Okay. Hasta la vista.